With one more example, just to solidify everything in our minds. So we have example 4. Now this time we will let f equal to 2xy and cosine of xy. Okay. Well, our task is to find the integral of f over c, where c is equal to the two curves c1 and c2, where c1 is equal to sine x and c2 is equal to sine 2x. And we would like x to range from 0 to pi. So let's go ahead and draw out what this region is. So we have the sine function, y equals sine x. This is 1 and negative 1, right? Let me go ahead and draw a little bigger here. So 2 is here. Let's see. 2 sine x. Actually, I think I have sine 2x, 2 sine x. Yes, I'm sorry. This is not sine 2x. This is 2 sine x. There we go. So sine 2x would actually end up giving me a different period. We're going to have the same period. So basically, I have sine 2x. It's going to be this one. It's going to be something like this. And we want to go from 0 to pi. So this is from 0 to pi. So this is the region right here. The region. So this is one curve. This is the other curve. So basically what they're asking me to do is we want to find the line integral of this vector field around this path. I haven't drawn it very well, but that's it. So instead of doing the line integral, we're going to use Green's theorem, and we're going to integrate this vector field over the area enclosed by that path. That's what we're doing. Okay, so let's go ahead and just work it out. Well, so this is f1 and this is f2. We want to find, so let me see, let's go ahead and do df2 dx. That's going to be, so if I take this, the derivative of this with respect to x, I'm going to get minus y times sine of xy. And if I take df1 dy, I'm going to end up with 2x. Therefore, my integrand, so this minus that, so my df2 dx minus df1 dy, which is my integrand under my double integral, is going to equal minus y times the sine of xy minus 2x. Okay, so now we're integrating x. So our line integral, of f over c is equal to, well, we're going from 0 to pi, so as far as x is concerned, it's going to be 0 to pi. And as far as y is concerned, the region is between the two graphs, sine of x and 2 sine x. We have minus y times the sine of xy minus 2x. That is our integrand. And then we have dy dx. And I'm actually going to let you work this out. Hopefully you have some mathematical software and see what that particular number is. Again, doing it is not as important as actually being able to take a particular problem, find a region, find the boundary of that region, decide what the upper and lower limits of integration are if you are in fact going to use the Green's theorem to solve a double integral instead of a line integral. We can certainly solve a line integral here. It's not a problem. We can parameterize both of these curves, do each one separately and add them, but we might as well avail ourselves of Green's theorem because it's there for us. We take df2 dx minus df1 dy, that's our integrand. We have our limits of integration, 0 to pi, sine x to 2 sine x, and that's about it. The rest is just a question of plugging it into your software and getting some number. So that's it. That is Green's theorem. Now, we're definitely going to have more to say about Green's theorem, no doubt about it. In fact, next lesson, we're going to go a little bit deeper and talk about two different versions of Green's theorem, something called the circulation curl version and something called the flux divergence version. Until then, thank you for joining us here at Educator.com. We'll see you next time. Bye-bye.